Okay, welcome everyone. This is roughly the midpoint of this course and the semester, and I'm about to embark on what I think are two of the really key arguments in this whole subject. So if this is the only lecture you remember from the entire course, it may be the right one. Let me just say what we are going to study and kind of situate it in the larger picture of other results that one might head to, some of which we will touch on before the end of the course, others of which are developed in the notes. So what we're studying right now is a hyperbolic surface. And let me, for convenience, say for the moment that it's compact, although many of the results will work for finite volume. And then on the unit tangent bundle, as we've been discussing, we have two nice flows, the geodesic flow and the horocycle flow. And the theorem that we're going to discuss today is that these flows are mixed. Now, the mixing of the geodesic flow should be almost intuitive. So the idea is that when you look at geodesics in hyperbolic space, because of negative curvature, if they're not asymptotic to one another, then they spread apart very rapidly. So if you take a small open set in the unit tangent bundle, then the vectors there, because this is open, they point in sort of an open interval of directions. And then when you start flowing, the geodesic going in one direction very quickly diverges from the geodesic going in the other direction. And diverges much more rapidly than it would in Euclidean space. They get exponentially far apart after time t. So it's not at all surprising, actually, that they become rather randomly distributed, and that's what this mixing captures. It's maybe a little less obvious that one should expect the horocycle flow to be mixing. But in fact, the horocycle flow turns out to have even more robust behavior than the geodesic flow. So there's another pair of theorems we will discuss, one of which is that, and this is really under the assumption that X is compact, every horocycle orbit is dense. And this is really kind of remarkable. It means that if you draw a horocycle upstairs on the hyperbolic plane, and then you just project it down onto your Riemann surface, then you get a dense subset of your Riemann surface, no matter which horocycle you draw. And in fact, it goes close to every point and in every possible direction. But there's an even stronger result than this, which is that, in fact, the horocycle flow is uniquely ergodic. And let me remind you what this means is that every horocycle orbit spends the right amount of time in any given open set, the amount of time being proportional to the measure of that open set. So remarkably, the horocycle flow is even more rigid or more chaotic or more well-behaved than the geodesic flow. And one should really compare these to their baby models. For this is an irrational rotation of S1, which we've also seen is uniquely ergodic. And for the geodesic flow, you might compare this to either a toral automorphism, a hyperbolic toral automorphism that behaves somewhat like this. And in fact, you'll remember that a hyperbolic toral automorphism interacted with an irrational rotation in a nice way. That was the Hopf argument, and that's what we're going to use to prove mixing. So these interacted by Hopf, and we will use a similar interaction to prove these results. Now, where do these results go? Well, the first result theorem, these are mixing. This is what I would call generic ergodic theory, because it tells you that a randomly chosen orbit is uniformly distributed. This unique ergodicity is much stronger. This is some sort of rigidity theorem, which tells you that every orbit is well behaved. And the generic behavior can be generalized nicely to hyperbolic n manifolds, so functions of hyperbolic n space, and it underpins a topic I will elucidate that I mentioned in the introduction to the course, namely Mostow rigidity. On the other hand, these results, especially the unique ergodicity, they're more recent, and they are ultimately subsumed under what's now called Ratner theory. We just call it Ratner's theorems, Ratner's proof of Raghunathan's conjectures. And these are very general results about unipotent actions, which we will formulate. And they lead, for example, to many other results, both geometric and arithmetic. For example, they lead to a description of the behavior of hyperbolic planes in hyperbolic n manifolds. It turns out planes in 3 manifolds are much better behaved than geodesics in 2 manifolds. And also to the behavior of quadratic forms, which I also announced at the beginning of the course, the Oppenheim conjecture. And finally, some of the ideas behind both of these results, they don't really have to do with ergodic theory. They have more to do with the unitary representations of the underlying group, SL2R. So there's a sort of a third current here, which is representations of SL2R and SLNR, unitary representations. And this somewhat more abstract current will lead into Kazhdan's property T, which underlies the theory of expanding graphs. Okay, so my goal for the remainder of these lectures is to develop these theorems in the case of surfaces so that we understand the most basic cases of unipotent and geodesic flows very, very clearly, and then give you at least a glimpse of these more general settings where the same arguments can be boosted or further developed to prove these deep and more modern results. Okay, so any questions before we dive in to this program? So I should also mention that there's a lot of interesting material that I'm trying to develop in the homework problems for this course, and I really encourage you to read the homework problems. You know, one way to read a math book, which I have to confess I did as an undergraduate, was you get a homework assignment, you read the homework problems, and then you leaf back through the book trying to figure out where the material is you need to do those problems. So if you were to do the problems at the end of the course notes and use the course notes as hints, that would be a very interesting way to absorb this material. So there's a lot of stuff going on in the problems that I hope you'll take a look at. Okay, and not just the ones that are assigned. There's more than 100 problems at the end. Okay, so let's embark on this study. So we'll start with this theorem. That is the mixing of the geodesic flow. And this will indeed just require that X is a finite volume. Okay, so the proof will go in several steps. So the first step is we will prove that the geodesic flow is ergodic. We will warm up to mixing by first proving ergodicity of the geodesic flow and then of the horocycle flow. So let's prove, let me call this 1 and 2. And then we'll prove 3 that the geodesic flow is mixing. And then we will prove a very strong version of the statement that the horocycle flow is mixing. Okay, so ergodicity of the geodesic flow. This proof is going to be very fast. Don't blink. And it should be familiar to you. This will be by the Hopf argument. So 1 is by the Hopf argument. Okay, so what do? We choose a function f that is, say, continuous and compactly supported on the unit tangent bundle of x. And let's say that the we want to study the ergodic averages of this with respect to the geodesic flow. So we form a function, f of little x, which is the limit as capital T goes to infinity of the usual thing, 1 over t, the integral from 0 to capital T, of the value of this function at x. And now I'm going to try to be careful here, apply the geodesic flow on the correct side. So remember, the unit tangent bundle is gamma mod g. So you should think of the geodesic flow as the action of the diagonal group acting on the right, dt. And this is for x in the unit tangent bundle, of course. So we take x in here. And now, by the ergodic theorem, that is the hard ergodic theorem, the pointwise ergodic theorem, it implies that f of x converges AE. And to prove ergodicity is the same thing as to show that the limit is constant. Because since the measure is preserved by gt, we have that the integral of capital F equals the integral of little f. So to finish the proof of ergodicity, we just have to show that this is constant AE because it's just a projection of little f to the space of gt invariant functions. That's what von Neumann's ergodic theorem says. So we need to show f of x is constant. Okay, now let's lift to the universal cover. So we're studying the geodesic flow down here on our surface. We've picked a vector x, and we form the geodesic that it generates, and we've averaged our function little f along a long piece of this geodesic and then taken the limit. That's what capital F is. So let's lift this to a function on the unit tangent bundle to h, just using the covering map down to t1 of x. So here we have our function capital F, and here we have its lift, f tilde. Now, the function f is constant along the orbits of the geodesic flow. Because if you start at a different point in the orbit, eventually the interval you're averaging over is almost the same as the interval of any other point. So this function is constant on orbits of the geodesic flow. So it's constant along any geodesic. But there's something even better. So if we draw a geodesic in the universal cover, and we think of this as defining a subset of the unit tangent bundle to the hyperbolic plane, then F is constant, F tilde is constant here. But so what that means is that the value of F tilde only depends on the points P and Q that describe the endpoints of the geodesic. So F tilde is really a function of P and Q, where P and Q are in the circle at infinity across itself with the diagonal removed. In other words, it's a function on the space of geodesics. Okay, now here's the beautiful property of this function. What if we had another geodesic that converges to the same point as the geodesic gamma? I claim that this other geodesic, which will start at a new point P prime, but converge to the same point Q, I claim that this function has the property that this is the same as F tilde of P prime Q. In other words, the value of the function doesn't depend on this endpoint of the geodesic. Okay, now why is this the case? Well, what does it mean for these two geodesics to converge to the same point on the circle? Just think about it in the upper half plane. Here's 2 points that both two geodesics, gamma, sorry, I should have called this gamma and maybe delta. Here's two geodesics, gamma and delta, that converge to the point at infinity. The distance between these geodesics at height y is, say, e to the minus y, if they're distance 1 apart. They converge exponentially fast. So when projected down to this Riemann surface, you have one geodesic moving along and another geodesic that starts far away, but eventually very closely tracks the original geodesic. So that means that you get two orbits of the geodesic flow, which are very close together when t is large. But remember, we're averaging a continuous function with compact support. So since F is uniformly continuous, once these geodesics are very close, the values of F along those geodesics are almost the same. And so this function doesn't actually depend on the first coordinate of the geodesic. It only depends on where the geodesic is heading in positive time. So it doesn't depend on P. Okay, now how do I complete the proof? Remember, all I need to show is that F tilde is constant. What's the punchline here?
It shouldn't depend on Q either.
Why not?
Because you can reverse the flow, right?
Exactly. Well put. You can reverse the flow. That's all there is to it. That's Hoff's brilliant argument, which we already saw in the case of a torus. Suppose we just were to redefine F by taking G minus T here, by flowing in the opposite direction along the geodesic. The ergodic theorem says that limit exists also. But the two limits agree almost everywhere, because what their value is the projection of little f to the space of GT invariant functions. That's what von Neumann's theorem says. So we could really call this F plus if we wanted, or more to the point, if we put a minus sign in here and put a minus sign in here, then we have that F is equal to F minus AE. And then we could take F minus tilde and apply exactly the same argument to conclude that this is also equal to F tilde of P Q prime for any other Q prime. That is, when if we change the forward coordinate without changing the backward coordinate, the backward endpoint of the geodesic, then we get the same averages going in negative time. And since these have to agree, the geodesic flow is ergodic. Okay, so this, as I said, this, if you want to remember one thing a year from now about this course, this is this beautiful Kopf argument. And the idea is that in these hyperbolic dynamical systems, like the geodesic flow, the future and the past are independent of one another. So when you average along an orbit, it doesn't depend on the past, but it also doesn't depend on the future, because you can average in the other direction. And so it doesn't depend on anything, and that gives ergodicity. So this failure of the early part of a geodesic to correlate well with the late part, this sensitive dependence on initial conditions, forces ergodicity of the geodesic flow. Okay, so you'll notice there was almost nothing to this proof. We used the ergodic theorem and not much else. And indeed, there are two versions of the ergodic theorem, the pointwise one and the von Neumann version. The von Neumann version is rather easy compared to the pointwise version, and we could have gotten away with just the von Neumann version here. So in fact, this argument is really quite elementary. Okay, so let's keep that in mind, that the geodesic flow is ergodic, and now let's try to show the horocycle flow is ergodic. Now the horocycle flow behaves very differently. A horocycle is not determined by two different points. Also, horocycles that are nearly parallel diverge very slowly. So we can't necessarily expect the same type of argument to apply. But there's a beautiful trick which will also apply when we prove mixing, which is that the horocycle flow and the geodesic flow interact in interesting ways. So let's think about how the horocycle flow and the geodesic flow are related. So let me just draw. Here's my basic vector pointing up at I. If I apply the horocycle flow for some time s to this point x, I guess I'm going back and forth between using subscripts and superscripts. If I look at hs of x, I will have flowed over to this vector here. But now there's another way to get to the same vector. It's to follow this geodesic. Right? So I could also get to this vector by using the geodesic flow. But I wouldn't apply the geodesic flow here. I'd have to first rotate the vector a little bit, so it's tangent to this geodesic. And then when I arrived at my destination, I'd also be pointing the wrong way. In fact, I'd almost be going 180 degrees from where I'd want to go. So I would need to rotate at the beginning, and I'd need to rotate at the end. And then I flow by some distance t, which is actually much shorter than s. This is the most efficient way to get from this point to this point. The horocycle flow takes a long time. So how can I write this how can I use this to relate hs and gt? Well, what this says is that hs is equal to what? So first, and I'm going to think of things again as acting on the left. So let's say xhs is equal to, you take x, and then you first rotate a little bit, which means you apply e theta for some small angle theta. And then you apply the geodesic flow for some time t. And then you apply, here you have to rotate back. And in fact, the amount you have to rotate back is just the complement of the amount you rotated at the beginning. So here you put e pi minus theta. So that's a relationship between the horocycle flow and the geodesic flow. And of course here, theta and t depend on s. But what happens when s gets very long? Theta tends to 0 as s goes to infinity, and t goes to infinity as s goes to infinity. Okay, so now I'm going to consider the action of these flows on L2 of T1 of x. And I'm going to consider a function here with the integral equal to 0. So I know that this function has the property, by ergodicity of the geodesic flow, that if I average it over a long geodesic, then it converges to 0, almost everywhere. And then I'm going to denote the operators coming from HS, GT, and E by HS, capital GT, and E theta here. Those are the corresponding operators on the space of L2 functions. So for example, HS applied to F at X is X HS is F of XHS. Okay. So now let's suppose that F is HS invariant. What does ergodicity of the horizontal flow mean? It means that there are no HS invariant vectors of mean 0. So what we want to show then is that F has to be equal to 0. So we want to show that F is equal to 0. Now, what we have is that HS, F, let me make sure I don't depart too much from my notes here. That HSF can be written as, so I'm going to take the inner product between HSF and G. And this, of course, will be the same as the inner product between G and F for every S, because F is HS invariant. But now using this equation, I can write this as the inner product between G and E, where's my equation? E theta, GT, E pi minus theta. And now what I'm going to do is I'm going to let T change, and T will determine S as well as theta. So these two quantities are equal, so if I were to put a 1 over capital T here, and then integrate from 0 to capital T, this expression dt, I would still have equality. And now we can move the E theta over to the G. So here, instead, I could write E minus theta applied to G, using the fact that this is a unitary operator. And then here, I would have GT applied to E to the pi minus theta, sorry, this should have been F here, dt. But even better, I can now move the integral inside. And regard this as the average of GT applied to this vector. But this vector is changing as with respect to T, because theta depends on T. Okay, what does this quantity converge to as capital T goes to infinity? Well, theta is tending to 0. So this quantity just converges to the ergodic averages of not quite F, but E pi times F. So this tends to 1 over T, the integral from 0 to T, or it's approximately equal when T is large, of GT applied to E pi F dt. And since the geodesic flow is ergodic, this converges to 0 by ergodicity of the geodesic flow. So this part of the inner product is converging to 0, And this part is some vector that's also converging. In fact, it's converging just to G. So this converges to G. This side converges to 0, but all along, they're just equal to GF. And so GF is equal to 0 for all G in our Hilbert space, and that implies that F is equal to 0. Okay, so what we see in this argument is that you can boost the analysis of the geodesic flow to an analysis of the horocycle flow, because the geodesic flow and the horocycle flow are somewhat similar up to the action of this compact group of rotations. Now there is a radical time change that takes place. T is, roughly speaking, like the logarithm of S here. But that doesn't matter, because for ergodicity, we just want to study vectors that are invariant under S. There's no, the behavior of S over time is kind of irrelevant, which is why we could average over T instead of S here. So that proves the horocycle flow is ergodic. Okay, so in summary, the first statement was true by the Hopf argument, and the second statement uses the fact that G is KAK. That is, in particular, we can write an element of N, we can factor it as 2 rotations times the geodesic flow. Okay, now the third argument, to prove mixing, this is one that I hope will be very familiar to you, because it's the one that we did for the torus twice, because it was a little tricky to get everything on the right side in the inner products. And it depends on a different type of interaction between the horocycle flow and the geodesic flow. So for 3, what we really use is the fact that the geodesic flow and the horocycle flow interact nicely. That is, A times N is a solvable group. Now, let me remark that this solvable group is extremely familiar to you and easy to understand. If you have an element A here and an element T here, then their product corresponds to the transformation x goes to AX plus T. If we think of this as A as being isomorphic to R plus, and N as being isomorphic to R. So it's just the group generated by multiplication and translation on the real line. That's how AN acts by Mobius transformations on the boundary of hyperbolic space. And what we know very well is that translations form a normal subgroup of this affine group. If you conjugate a translation by multiplication, you just get a different translation. So A normalizes N. That is, A inverse is equal to N for any element of the diagonal group. Now, what's the actual formula for that normalization geometrically? The actual formula is following. Again, it's something that we can see very nicely in a picture. So I'll take my standard vector again at I. And now I want to compare applying the horocycle flow and the geodesic flow. So let me first apply the horocycle flow for time s. So this is my vector x, and this is hs of x. So this distance here is literally s, because I'm at height y is equal to 1. Now alternatively, I could apply the geodesic flow for time t. And that would bring me up to this vector here. This is gt. And what's the height of this vector? What's the y coordinate of this point? Who can tell me? the distance from here to here should be t in the hyperbolic metric.
E to the t?
Yeah, exactly. So the multiplicative group is the distance between 2 points on the imaginary axis is the logarithm of the ratio of their y-coordinates. So you can think of g as, roughly speaking, doubling the y-coordinate after every unit time. So this is up way up here at height y is equal to e to the t. And now we can apply the horizontal flow here and the geodesic flow here. So this point has to go up the same distance as this point did to reach this vector. So this point here can be described by saying we do gt hs of x. But we can also go this way. We can go up by gt and then over by the horizontal flow. But how long is this segment? Well, the hyperbolic metric is dz over y. So this segment is much shorter than this segment. In fact, it's shorter by a factor of e to the minus t. So this distance is e to the minus t times s, not s anymore. And so what we find is that to go the other way, we first apply the geodesic flow, and then we apply the horizontal flow, but only for time e to the minus ts. So h e to the minus ts times gt is equal to gt hs. So what you see here is that if you move the gt over to the other side, gt conjugates the horizontal flow into itself, but it makes a radical time change. It contracts the time by a factor of e to the minus t. So let me change this around a little bit and write it in terms of operators, because that's how we're going to do the argument. So the corresponding operators satisfy, and now I'm going to change it slightly, as I said. So they satisfy gt, and now I'm going to put here h s e to the t is equal to hs gt. And that should remind you of what we did in the case of a hyperbolic torial automorphism, where we had the property that t to the n applied to hs was h lambda to the n s times t to the n. So this argument, the use of the fact that the geodesic flow normalizes the horizontal flow, is again part of the Hop argument. Okay. So we can now just mimic the Hop argument to prove mixing exactly as we did before. Unfortunately, I have to erase something to write down that proof. So here you go. The main thing we need is just this equation at this point. Yes?
I have a question.
Yes.
In the equation that you wrote down for, shouldn't a and n act on x from the right?
So that's a good point. So everything is up to possibly reversing the order of the composition of the operators. So unfortunately, my dyslexia is especially acute in the front of the class. It's slightly milder in the notes, but it's probably still there. But the argument is insensitive to getting the order right, because it's either this way or that way. But you raise a good point. And it's always complicated. For example, if you want to make a group action, if you want to write a times f of x, you should write this as f of a inverse x, if you happen to be acting on the left. Otherwise, you don't get a group action. So there are right and left issues all over the place. Thank you for drawing my attention to them so I can sweep them under the rug. Other questions? Okay. So, so let's go back to this equation here, and what we're going to do is, remember, we have the fact that the horocycle flow is ergodic now. So that means it's useful to consider this operator where we average over a segment of the horocycle flow. So I'm going to define a new operator built out of HS, which is you take 1 over 2s times the integral from minus s to s of, let's call it HU of f du. And by the ergodic theorem, this tends to 0 as s goes to infinity for all f in L2 naught of T1 of s. Also, since we average between forward and backward time, it's symmetric in time. So a second property it has is that it's equal to its own adjoint. And then the third property, which is often the key to the proof, is if you take a vector and you average it for a very small time, then it barely moves. So SS of f tends to f as s goes to 0. And then since S is built out of HS, it satisfies the same equation that I've written down here. So we can just put S in here instead of H. Okay, and so now we just need to do the Hopf argument. And the method I've discovered that should help defeat the possible dyslexic issues is to start in the middle using this identity and then work back towards the ends. So what we get using this identity is that if we take any two f and g in L2 naught of T1, then we have that SS GT F G is equal to, and then we just commute it over, GT S S ET F G. Okay, and now we move the G over on this side, and we get S e to the T F, comma, G T inverse G. Now, what can we say about this last expression? So what we're doing here is we're going to fix S small. And it's going to be small enough that we can apply C, as we'll see in a moment. But after we fixed S small, we let T go to infinity. And then what happens is, since S is positive at least, this index here, the amount of time you're averaging, goes to infinity. And so that vector tends to 0 by ergodicity of the horocycle flow. So this goes to 0. And this guy, we don't know what it's doing. It's being moved around by the geodesic flow, but its norm remains 1. So since this, its norm remains constant. So this has the same norm as G did all along, and so the inner product tends to 0. Now, how's that related to mixing? Well, now we work on the equation going the other way. This is just equal to, putting the SS on the other side, GTF SSG. And if we choose S very small, then this is almost the same as GTFG. And so what we've shown is that as T goes to infinity, the pairing between GTF and G goes to 0. And that's exactly what mixing says. If you take two vectors of mean 0, push one along by the geodesic flow, its average against any other vector of mean 0 tends to 0. So this is mixing. Okay. And again, this is the Hop argument, and it's the basic idea, which is really quite beautiful, is you use two properties of averaging. The small time property is this one. Doing a little averaging barely changes your function. And the large time property is this. Ergodicity says what happens in large time. The averages go to 0. But the geodesic flow converts large time to small time, and that's what forces mixing. Now, another way to say this, just a little bit intuitively, is that when you start with your function f, I'm just going to write this, or can I write this as the intuition behind mixing. So the intuition is roughly speaking that f starts out having some sort of Fourier transform. Imagine it's sort of like some sort of sine wave or eigenfunction of the Laplacian. But when you apply the geodesic flow to f, what happens is the frequency is radically changed. And the reason the frequency is radically changed is because of the fact that geodesics diverge very rapidly. So if f was oscillating just a little bit here, then when you pull it back by the geodesic flow, it oscillates very rapidly here. So the Fourier transform components of f, or the rate of oscillation, moves off to infinity. And when you integrate this function against this function, you get 0, because the averages, everything kind of cancels out when you take the product, or they're almost orthogonal as elements of L2. So that's a little bit of the intuition behind this, this mixing of the geodesic flow. Okay, finally, how do we prove the horocycle flow is ergodic? And this is mixing rather. And this is kind of remarkable, especially for how easy it is. In fact, we're going to prove something weaker, much stronger than mixing of the horocycle flow. And the proof here is going to again use G is KAK. So in fact, this rather deep theorem can be summarized as saying you use the Hop argument's two elements and you use G equals KAK twice. And that's enough to reconstruct the proof. Okay, so what's the stronger statement that we're going to prove? We're going to prove that G is mixing. So what does it mean to say G is mixing? It means that if you have a sequence, Gn in G, and Gn goes to infinity, and then you have any two elements, F1 and F2, of mean 0 on T1 of x, then the inner product between Gn of F1 and F2 goes to 0. Again, if these were not of mean 0, then Gn F1, F2 would converge to the integral of f times the integral of F1 times the integral of F2. These functions would decouple, and mixing would just give the product of their integrals. If they were the indicator functions of measurable sets, then the image of one under Gn would intersect the other one in roughly the product of their measures. And the hypothesis here is just that Gn goes to infinity in the group G. Now you might ask, what does it mean to say a sequence of group elements goes to infinity? Who can give me a definition of that hypothesis?
Does it mean that the sequence leaves every compact set?
Yeah, exactly. So in any locally compact space, like a finite dimensional manifold, what it means to say a sequence goes to infinity is it has no convergent subsequence. So in other words, it eventually leaves every compact subset of G. So this means it leaves every compact subsets of G. Okay. So of course this will be much stronger because if to prove the horizontal flow is mixing, you have to show that HSF1, F2 tends to 0 as S goes to infinity. And that's just a special case of an arbitrary element in the group going to infinity. Okay, well, the proof of this is almost embarrassingly easy. So, so for the proof, we write Gn as Kn, An, Kn prime, in K and K. Now, Gn is going to infinity, and these Kn's are ranging in this compact set. So we must have that An goes to infinity in A. Now, furthermore, this sequence of inner products is bounded by the product of the norms of F1 and F2. So we can pass to a subsequence so it converges to a limit. So let's just assume that, that Gn F1 F2 converges to some limit L. And what we want to show is that L is equal to 0. Because if that's true for every limit, then the whole sequence must converge. Okay, now, once we got this converging, we can pass to a further subsequence so that these elements in the compact groups converge. So we can also assume that Kn tends to some limiting element K in the rotation group, and Kn prime tends to some K prime in the same group. Whereas An is going off to infinity in A. And now, again, don't blink. So Gn F1 F2, this is equal to Kn An Kn prime F1 F2. And now, as usual, we use the fact that these operators are unitary. So this is the same as An Kn prime F1 Kn F2. With an inverse here. But this term just converges to K inverse F2. That's some fixed vector. This term here converges to K prime F1. K prime F1. And so in the limit, this has the same limit as An applied to K prime F1, comma, K inverse F2. Well, we can forget where these vectors came from. This inner product has the form of An Fg for two specific elements. Maybe I should call this. Yeah, this is F1. So the two specific elements of mean 0, and An is going to infinity. And so this goes to 0 by mixing of A. And so indeed, the entire group is mixing as soon as the geodesic flow is mixing. And the argument uses nothing about hyperbolic geometry. It uses very simply the fact that the group has this factorization. So we will eventually see that this is a profound property of unitary representations of SL2R. It doesn't have anything to do really with hyperbolic geometry. When you have SL2R acting, as soon as A is ergodic, the whole group is mixing, and in particular, A is mixing. So things like the geodesic flow are almost automatically mixing once they're ergodic because they're part of an action of SL2R. That's something we'll develop more formally in the sequel. Okay, but there's the proof. This is the basic ergodic theory of the geodesic and horocycle flows on a hyperbolic surface. Okay, let me just make a couple of remarks. So we haven't said much about hyperbolic N manifolds, but as you can imagine, everything we talked about works just as easily in hyperbolic space of dimension n as it does in hyperbolic space of dimension 2. For example, the first step in the argument. The first step in the argument in higher dimensions just uses the fact that a geodesic in Hn is determined by its endpoints on the sphere at infinity. So again, you get a P and a Q, and then using the Hopf argument, you get that the geodesic flow is ergodic. So let me just mention that here, that this theorem, which I'll now amplify, is saying, in fact, G is mixing. Works also for the unit tangent bundle of Mn, where Mn is gamma mod Hn, hyperbolic N manifold, and in fact, it works for the frame bundle. That is the set of orthonormal frames, Fmn over Mn. And indeed, the frame bundle in this case is the right interpretation of gamma mod G, where G is now SON1. Okay, so in all of these cases of finite volume hyperbolic manifolds, we have mixing of the geodesic flow and mixing of all of the non-compact one-parameter subgroups of the correspondingly group G. Okay. Let me just give you one more simple corollary just to emphasize how powerful this result is. So suppose I take a transformation from the unit tangent bundle to itself by just taking the geodesic flow for time t. Rather than taking the whole flow, just at every point move the vector ahead by a distance of 10. So let's let t be the time t naught greater than 0 geodesic flow. So this is also ergodic and mixing. When t is the time t naught geodesic flow, or t is the time t naught horocycle flow. So if you discretize these flows, you don't lose these strong mixing properties. That's actually a general property of flows. Once you prove mixing, any non-compact subgroup is also mixing. Okay, so the next topic is going to be not the measure theory of these flows, but the topology. So let me formulate the statement that we're going to establish again. So our next point of study is the topology of the geodesic and horocycle flows. And the theorem that we'll prove first is that if X is a compact hyperbolic surface, then every horocycle orbit in the unit tangent bundle of X is dense. This is, people say, when you have a dynamical system and every orbit is dense, you say that corresponding flow is minimal. So the horocycle flow is minimal. Minimal means there is no smaller closed invariant set. It's sort of like the topological version of ergodic. So the first thing to do before proving this theorem is let's contrast it to the geodesic flow. Does the geodesic flow have the property that every orbit is dense? Well, certainly not. For the geodesic flow on X, as we've seen, every homotopy class on X, other than the trivial one, is represented by a closed geodesic. So there's millions of closed geodesics all over X, and each of these gives an orbit of the geodesic flow which is not dense. This is very similar to the fact that for an endomorphism of the torus, the points of order n, which form a finite set, were preserved and permuted amongst one another. So their orbits can't possibly be dense. So in the geodesic flow, there are lots of non-dense orbits, lots of closed orbits. And in fact, closed orbits of GT are dense in T1 of X. That is, given any vector, you can move it just a little bit so it becomes tangent to a closed geodesic. That geodesic may be very long, but is nevertheless closed. And there's various ways to prove this. Maybe I'll delay the proof for right now, where it fits in more naturally with the theory of Monster rigidity. But you also might think to yourself, do I believe that this is true? And if so, why? And also, could I prove this directly? For example, in the case of SL2Z. This is true, in fact, for finite volume surfaces as well, that closed orbits are dense. So you might just ask yourself why. In fact, this may be an upcoming exercise. For example, you see this directly in the case of SL2Z, one of our most concrete examples of a lattice in SL2R. Okay, so the geodesic flow is very different from this, and I shouldn't leave you with the impression that every geodesic is either closed or dense. It's really a mess what can happen for closed geodesics, because for the geodesic flow, because once you have a closed geodesic, you can have a geodesic which spirals towards it in future time like this. And maybe it spirals towards a different geodesic in reverse time. And then if you take the closure, you get something that looks intrinsically like this. There's a non-compact spring going from one circle to another. And the geodesic flow has a periodic cycle here, a periodic cycle here, and a non-periodic cycle here, one that's dense in this spring as a whole. And if I delete this, I get a smaller set that's invariant under the geodesic flow. And if I delete this, I get a still smaller one. So this locus is not even minimal, what I get when I take the closure of one geodesic, one orbit of the geodesic flow. And in fact, there's very complicated minimal subsets for the geodesic flow. I should also say that, of course, if we were to replace the horocycle flow by the elliptic flow, by the rotation of vectors, then this would be nowhere close to being true. For the compact group, the rotation group, every orbit is closed. And so there are no dense orbits. And somehow, as you take a rotation and you make the circle larger and larger, you eventually get to the horocycle flow. And then if you keep going, you get to the geodesic flow. And you start with this completely tame behavior with the elliptic flow. And when you reach the geodesic flow, you have complete chaos and all sorts of weird behavior of orbits. But right at the boundary where the phase transition is occurring, right at the horocycle flow, you have this rigidity. Every orbit behaves in the same way, way, they're all dense. Okay, so let's prepare for the proof of this theorem. So in preparation for the proof, I could give the proof like really fast, but there is an idea in the proof which is pervasive in homogeneous dynamics, and I want to take this occasion to exposit that idea. Often this idea is buried at the bottom of proofs, and it deserves to be brought to the surface. And so that's the idea of double cosets. Okay, so the general setting is we have a Lie group G, and we think of this as somehow corresponding to a geometry. And then within G, we have a subgroup H, somehow corresponding to a geometric object. And we'll see what this means in examples, but you already know G is SL2R, K, A, and N correspond to geometric objects. And then G mod H is the space of all of these geometric objects. H itself is the stabilizer of one geometric object, like a point or a geodesic, and then the coset space describes all of them. But what about the space of pairs of geometric objects of the same type? How do you describe that? So the space of pairs of geometric objects, which I'll call the configuration space, is just the product of two copies of the space. So G mod H cross G mod H is the space of, and let me call this the configuration space of pairs of geometric objects. And now what we want to do is we want to analyze how one geometric object can sit with respect to another from an intrinsic point of view. So we want to know, what are the invariants of the space of pairs of objects? What natural quantities can we measure when we have two geodesics, or we have 2 points, or we have 2 horocycles? And so the moduli space of pairs is obtained by taking the quotient of this space by the action of the group of isometries. So this configuration space modulo isometries is equal to what's called the moduli space of pairs. And the way you form the moduli space is you take the configuration space and then you mod out by G acting diagonally on this product. You have 2 geometric objects, you can move them both by an isometry. That's not going to change any intrinsic invariant describing their relationship. So from the point of view of Lie groups, that means we mod out by the left action of G on this product of groups. And what do we get when we mod out? Well, what happens is one of the G's disappears. And the result is the double coset space H mod G mod H. And indeed, the map is, if you take an element specified by G1 and G2 here, that is the coset G1H and the coset G2H, you can associate to that the element G2 inverse G1. And G1 is well defined up to multiplying by H on one side, and G2 inverse by multiplying on the other side. So this double coset space can be interpreted as the moduli space of pairs of objects whose geometric type is described by H. In other words, whose stabilizers are H. And indeed, you don't even have to take the same type of object. You could take 2 different types of geometric objects, like a point and a geodesic, and then their relationship, their moduli space, would be described by a double coset space with different groups acting on each side. And let me remind you what this space is. So this space is to start out with, it's a topological space, as is this, because this is a topological group, this is a closed subgroup. So in general, this is a nice space. It's a manifold, it's a homogeneous space. It has an invariant measure on it when H is unimodular, all sorts of good stuff. This space is a wild space, sometimes, potentially wild. And it consists of the orbits of H1 acting on G mod H2. And we'll see that potential wildness in examples. And in fact, the potential wildness is going to be key to the proof of some of the main theorems, such as the one about the horocycle flow. Okay, so let's do some examples. So G is SL2R, plus or minus the identity. And for H, we can take K, A, or N. And what do these groups correspond to? Geometrically, these correspond to points in the upper half plane. These correspond to geodesics in the upper half plane. And this one corresponds to horocycles in the upper half plane. These groups being the stabilizers, respectively, of those kinds of objects. Okay, so what is the moduli space of pairs of points? Well, it's supposed to be this quotient, G mod K, K acting on both sides. So let's form that quotient a little bit at a time. So G mod K is the configuration space of single points. And as we see, that's naturally isomorphic to the upper half plane. Okay, so the double coset space is going to be a quotient of the upper half plane. And what do? We let K act on the upper half plane. We let it act on the left on G mod K. And what does that action look like? Well, K in the disk model is just the stabilizer of the origin. And the isometry stabilizing the origin are just rotations. So the orbits Kx in H, which is G mod K, are nothing more than circles centered at the origin. So what do you get when you take the quotient of the unit disk by rotation? Well, you get this space of circles centered at the origin, including the origin itself. So the quotient, K mod G mod K, is isomorphic to a half open interval, or if you like, the non-negative real numbers. In fact, if we draw a segment here that starts at 0 and goes off to the boundary of the disk, that meets each K orbit exactly once. And how shall we describe a given K orbit? Well, why not just take the hyperbolic distance from the origin to a given point on that orbit? So indeed, K mod G mod K is isomorphic by the distance function to the interval from 0 to infinity. And this isomorphism can be thought as follows. An element of G mod K corresponds to a pair of points, PQ and H, up to the action of the isometry group of H. And if you give me a pair of points, I can associate to them the hyperbolic distance between them. And moreover, if you give me 2 points that are the same distance apart, I can find a hyperbolic isometry that moves one to the other. So this double coset space is isomorphic by the distance function to the non-negative real axis. Okay, so that's the simplest case. The moduli space of pairs of points corresponds to, under the distance function, to their distance. That's the only invariant of a pair of points. And similar things would happen if we chose, for example, a point in a geodesic. If you're given a point in an oriented geodesic, then there's also only one invariant you can think of, which is the distance between the geodesic and the point. And so something like K mod G mod A also has a good model. But in this case, I should note that there is a sign because since this geodesic is oriented, it might be that the point lies to the right or the left. And so this space is isomorphic to the real line. And there's really a bijection between the moduli space of double cosets here and points on the real line. Any two, if a point and a geodesic are at a given sign distance delta, you can move that configuration to any other configuration with the same invariant by an isometry. Where it gets hairy is when we look at something like G mod A mod A. So what's going to happen when we look at, say, G mod A mod A? Well, now we're looking at the configuration space of pairs of geodesics. And there's a couple of things that might happen. One thing is the geodesics might meet. Another thing is that they might not meet, and they might have some sort of distance between them. But what's really scary in this space, what's really different from what happens when one of the groups is compact, is that as the distance between these two geodesics goes to 0, there's two things that could happen depending on where you stand. If you stand on their common bisector, that is their perpendicular bisector, or this shortest distance arc joining them, if you stand at this point as they get closer and closer together, in the limit they'll become the same geodesic. But if you stand far away from this point, you might just consider a geodesic here with a fixed endpoint, and then another geodesic here with endpoints P and Q. Here we have endpoints P and prime and Q prime. And as Q goes to Q prime, the distance between these geodesics goes to 0. But in the limit, they don't become the same geodesic. They become a pair of geodesics that are parallel. That is, they're asymptotic at infinity, even though they're not equal. And that distinction, the fact that as the distance between a pair of geodesics goes to 0, they could either coincide in the limit or simply become parallel, that belies the fact that this space is not Hausdorff. And because it's not Hausdorff, limits are not unique. So I'll expand on that failure of uniqueness next time, and then we will exploit it to prove Hedlund's theorem about minimality of the Horus cycle. Okay.